Yeah, so as Sam said, I'm going to talk about, so the title of my talk is on local Galois deformation rings. And yeah, as Sam said, which I didn't put in my title, I'm going to explain what this means in a bit, but this is local L equals P Galois deformation rings to distinguish the primes. And yeah, so everything that I say in this talk is joint work with Gerhard Böckle and Vitas Paškūnas. Okay, so what are we interested in? So we're interested in, I guess, the representation theory. Representation theory of Galois groups, as the title suggests, of p-adic local fields. And we're interested in the representations of this group taking values in modules that have mod p and p-adic coefficients. So the L equals P in the title alludes to the fact that this P is the same as this P. So I mean, like in the L not equals a P case, you'll take a p-adic local field and you'll look at mod L coefficients and L-adic coefficients, and then the theory changes quite a bit because the topologies are kind of incompatible, but in this case, they're very much compatible, which has a big influence on the theory. Okay, so let me set up some notation. So have to put down here. So some notation. So first, we care about the Galois group of a p-adic local field. So let F be a finite extension of the p-adic numbers. And for this talk, the kind of main object of study is what I'll call GF, which is the absolute Galois group of F. So fix an algebraic closure and look at the automorphisms which fix F. And right, so as I said, I care about representations of this group with mod p and p-adic coefficients. And so for that, so okay, I've said something about the group. For the coefficients, I'll just kind of fix a bit of notation. So L here is going to be some further extension of F, so a further finite extension of F. And I'll assume for technical reasons that that they're not so important really, that this contains the Galois closure of F. I mean, basically L is some auxiliary field, and the only requirement is that it's really big. It just has to, it has to contain, for most of the talk, it just has to contain like as many roots of unity of power p as F does, but I mean, later in the talk, it'll be useful to have this assumption. I mean, if you want, ideally I would want L to just be QP bar, but okay, I also want it to be finite, so. Okay, so, so then the main thing that we want to do is start with something which I'll denote by rho bar, which is a continuous representation. So, right, this group is a profinite group, so it has a topology, and I take continuous representations of this group valued in GLN of K. Sorry, I forgot to say that. So L is some p-adic field, O is going to be the ring of integers, and K, which I'll write as O mod pi, is the residue field. Okay. So rho bar is some mod p representation, right? It takes values in some finite field of characteristic p. And we want to, so I want to lift, so as I said, this is continuous, and I want to lift it to representations of GF in GLN of O. Okay. And the reason that you might want to do something like this, so the kind of motivation for why this problem arises comes from modularity lifting theorems. So basically, in the Langland's program, you have this problem of taking a Galois representation, which really takes values in a p-adic field, and trying to show that it comes from something automorphic. So in this,
You don't have to wear a mask if you don't want. I don't know. So did someone tell you?
I did.
all right,
You may take your mask off if you would like.
cool. Yeah, maybe I'll do that. Thanks. Yeah, so the motivation comes from modularity lifting. So in that setting, instead of f over qp, you typically look at like some finite extension of q, and then you look at its Galois group, and you look at some mod p representation of the Galois group of E. But then, okay, then this is more complicated because like you have to put local conditions at all the different primes, all the decomposition groups. And then those Galois representations, like typically the way this works is that you start with something mod p, and then you know a priori that one of its lifts comes from some automorphic form. And then you want to show that every single lift comes from an automorphic form. So this is the content of what is usually called a modularity lifting, or sometimes an R equals T theorem. Okay. So this is like kind of why you'd be interested in these things. And our hope eventually is that our results will have some kind of bearing on theorems in this direction. But yeah, I mean, like everything today is going to be local. Everything today. So all the statements and all the proofs is really local. Like we're not concerning ourselves at all today with like number fields from the Galois groups. Yeah, so that's just meant to be a word of motivation for why you would care about doing any of this. Any questions? Cool, and yeah, feel free to interrupt me whenever. If you like. Okay, so let me define the main objects of study. So, right, so I said that what we want to do is start with a row bar and then lift it to these integral representations, which are valued in O. And eventually we also want to invert P and then look at things valued in p-adic fields. And so if you want to study the ways that you can lift this, the convenient thing to do is try to construct an object which parameterizes all of the lifts at once. Okay, so let me give the kind of standard way to do this. So I'm going to define a category which I call no for Noetherian and then the subscript O. So this denotes a category of pairs. We're called A and phi of A. So A is a complete local Noetherian ring. And phi of A is a surjective map from A to K. So K is the residue field of O. And so in particular, A mod maximal ideal is then isomorphic to K. And yeah, so for example, you could take A to be something like O, the ring of integers. And I want to, okay, so this is a category where the objects are pairs like this, and then the morphisms are kind of the natural thing. So map A to B should satisfy the property that if you look at the map phi of A and phi B, this diagram should commute. And in particular, if this diagram commutes just because it's a surjection onto this finite field, these are automatically local homomorphisms of local rings.
You don't want A to be in O algebra, just a ring?
Yes, sorry, that is very important. Yes, I want this to be. Yeah, so it's a completely local Noetherian O algebra with a surjection onto the residue field of O. And the main example to keep in mind, like of objects in this category that will be important are things like O, right? I mean, K is an object in this category. Something like K power series X, let's say mod X squared. I mean, there's lots of different things you can cook up which live in this category. In fact, all of them, there's a structure theorem for things in this category. So they're all actually isomorphic to things that look like a finite power series over O, and then I mod out by some proper ideal. So everything in this, I mean, this category looks kind of, abstract, but it's actually just things of this form. you can prove that everything looks like that. And so I guess the idea is that you're starting with rho bar, which is just valued in K, and we want to study lifts of rho bar to O, and rings like this allow you to look at like families of lifts to O. So if I take a representation valued in something like this, then I can specialize all the variables x1 to xn into, let's say, O, and then you get a specific representation. And so this is a kind of way of putting together all the lifts into some kind of like formal algebraic family is kind of the way that I would think about it. Okay. Right, so then the basic object of study is what's called the universal lifting ring or framed deformation ring, whichever you like. So the universal lifting ring or framed deformation ring. So the distinction in this terminology is that really when you do modularity lifting theorems, you look at this. This functor is going to parameterize representations plus the choice of a basis. But oftentimes you don't actually care about the basis, and so you sort of mod out by conjugation. But for my talk, I'm always remembering the basis. The universal lifting functor. So what is this? This is a functor, which I call D rho bar, and I put a square. So the square denotes this thing about the basis. This is a functor from this category of Noetherian rings to sets. And it takes one of these pairs A phi A to, well, I want to lift to representations valued in these rings. So I take rho from GF to GLN of A, and then I require that this factors, or this, well, it lifts rho bar. So I have so I have the representation on top, GF, and then I have rho bar, which is a representation with K coefficients, and then this map is the reduction map given by A. Okay, so this functor takes one of these pairs to the set of representations which lift rho bar with coefficients in this ring. Right. And yeah, this diagram. Okay, so once you define this functor, the first basic result is that this functor d rho bar square is representable. Okay, so this is kind of there's multiple ways to prove this. I mean, one way is to write this profinite group as an inverse limit of finite groups, solve the same problem for all the finite groups, and then take an inverse limit, roughly. The other way is to use a more abstract criterion from deformation theory called Schlesinger's criterion, which is gives you a kind of less concrete way of constructing this thing. But there's different ways of seeing that this is true. And yeah, one way is more explicit, one way is a little less explicit. But what does this mean? So this means that there exists some ring R rho bar square. So R is replacing D in this category of the theory no algebras, such that it's representable. So if I take the value of this functor on any A, this is just the Homs from R bar square to A, and this also comes with a universal representation. So, right, so there's a universal element in this representable functor, and it's denoted by rho square, and this is, yeah, sorry, I should also say that these are all required to be continuous. So GF is profinite, and then A has the topology of the m-adic topology for its maximal ideal. Okay, so rho square is the universal representation, which lands in GLN of R rho bar square. And yeah, I mean, it's universal in the sense that if I take any other map to to GLN of A, then there's an associated map that there's associated map from R to A, which makes this diagram. Okay.
Just because I don't know, like, does the continuity not follow from like finite kernel or something?
It's not always going to have finite.
Sorry, cofinite kernel. Like, I mean,
It doesn't usually.
no, it doesn't follow from that. Okay.
No, I mean, we're not assuming that it has cofinite.
Okay.
Yeah, I mean, if you start with a finite field, then the finite field has the discrete topology, but in general for a complete local ring, yeah, they won't always be
the topologies on the rings involved are usually compatible with the topology, like a per-finite topology on the.
Yeah, so then the goal of the talk, or the goal of our work really, is to study the geometry of, well, I mean, yeah, I guess let me just say spec of R bar square. I mean, yeah, there are other things that you all want to understand, so are there other ways that you can kind of think of this? So like, yeah, I mean, we want to sort of understand the ring theoretic properties of R rho bar square, or the geometry or spec of this thing, or like alternatively, if you view this as a formal scheme with its maximal ideal topology, then there's an associated rigid space, and you can also try to understand that. There's a lot of different geometric ways to think about this thing, but yeah, our basic interest is to understand, like, what does this look like? What do its components look like? How well behaved is it, et cetera. Right. So let me make one quick remark, which I need to make in order to state the theorem properly. So yeah, so I mean, earlier in the talk, I said that I'm interested in lifting mod p coefficients to sort of integral coefficients, but of course we also care about what happens when you invert p. So one remark is that any surjection, so if I take the universal lifting ring, yeah, sorry, this thing is called the universal lifting. And I shouldn't have put the word universal up there. I realize now. But yeah, so this is the universal lifting ring representing the lifting functor. And any surjection of R rho bar square, if you invert pi onto, let's call it K. So here K over L is some finite extension. So basically any point of the spec of this ring valued in a p-adic field. Well, what can you do? I mean, you can take the universal representation rho square into GLN of R rho bar square, and then you can compose it with, well, first you invert P and then you compose it with F, and then you get something valued in GLN of K, and X. Space. And so if I mean, the functor, strictly speaking, only gives you representations valued in integral things, but of course, if you invert P in this ring and you have a surjection like this, you can just take the representation, just push the coefficients along the surjection, and you get a p-adic representation. The kind of nice thing is that conversely, any maximal ideal in this sort of scheme theoretic generic fiber, so any point in the scheme theoretic generic fiber has residue fields finite dimensional over okay, so like the points in this ring really all give rise to p-adic representations, which I mean, I guess the defining property of these representations is that they contain some lattice, which when you reduce mod this lattice, you get rho bar that we started with, or maybe slightly extended scalars to some bigger finite field or something. Yeah. And the other remark I wanted to make is that, so this, so this deformation ring is a way of kind of understanding the space of p-adic representations, where when you look at their mod p reduction, you get rho bar. Maybe, okay, strictly speaking, I should say up to semi-simplification or something, but this is the idea. And then there are, so you can, I mean, you can kind of wonder like, what if you let rho bar vary, right? Like instead of just looking at a single rho bar, what if you look at families of mod p representations? And actually, in some precise sense, which I'm not really going to get into, these can be sort of glued together into a kind of moduli space. Well, really, it's a moduli stack of mod p-adic representations. And this is due to relatively recent work of Matt Emerton and Toby G. So strictly speaking, they don't work with mod p rep, like they don't work with representations. They work with some kind of replacement for them called phi gamma modules or tal phi gamma modules. But they give a kind of they give some formalism that lets you take these rings and kind of glue them together into some sort of global object, which keeps track of all the sort of mod p representations. And for those who are familiar with the language of stacks, these things are versal rings to certain points in those stacks. So they kind of play the role of complete local rings at points in this modular space or moduli stack. Right, so this is the ring we care about. And yeah, we want to understand its structure. So maybe before jumping into the general case, right? I mean, n here is just any integer, so I can make these dimensions as high as I want. But maybe instead of doing that, I'll first give an example in the simplest case when you take n equal to 1. So what happens if you try to deform a mod p character of the Galois group, right? Okay, so fix, I'll call it psi bar. So psi bar is a character of GF, or really it's a Booleanization to K cross. Okay, so then how do I understand this ring R psi bar squared? How do I like deform this thing? Well, I mean, you can do this in a couple steps. So I'll sketch how you do this. So by twisting, basically, since you're in the one-dimensional case, you can sort of twist away this mod p character and assume that psi bar is actually just a trivial character, right? Okay, so you can reduce this to somehow by twisting to understanding just the deformation ring of the trivial character, and then if you look at any lift, which I'll call psi, from the abelianized Galois group to A cross, where now A here is one of these complete local Noetherian O algebras with residue field K. Then since it has to commute, I mean, since this thing has to commute with the diagram to K cross, psi actually lands in 1 plus the maximal ideal of A, right? I mean, it sort of lands in the kernel of this map because this should be trivial. But this thing is actually pro P, right? So since A is one of these nice objects, this is a pro P group. If A is Artinian, this is a P group. And so that means that psi doesn't just factor through the abelianization, but it also factors through the maximal pro P quotient of the abelianization into A cross. Okay. And now you can take this map and you can extend it to a map from the completed group ring. So you sort of take the group ring of all the finite quotients, quotients of this group, and then you take the inverse limit and you get this completed group ring. So you can show that this extends to a map like this, and it turns out that this thing is equal to is isomorphic to the deformation ring. Okay. So in the case n equals 1, it's like relatively simple because now you can use local class field theory and you can like write down what this is explicitly. So yeah, so by local class field theory, this deformation ring is just isomorphic to Well, first you can take just the usual group ring over something I'll call mu, which I'll explain in a second. And then you get a bunch of power series variables corresponding to kind of the copies of ZP in this group once you use class field theory. And the number of variables is the kind of, it's the degree of f over q plus 1. Okay, and here mu is equal to what I'll denote as mu p infinity f, and this is the group of p power roots of unity of 1 in f. Okay, so this is some finite group depending on f of order of p power order. Okay. Any questions about this example?
What do the different variables correspond to? I mean, one of them is the uniformizer, I guess.
Yeah, right. I guess they correspond to, like, when you
I guess, but it's clear,
yeah, when you like via local,
it's just the units.
yeah, it's the units. Yeah, it's the structure of the units in the field. Yeah, each of these corresponds to one of the copies of ZP that you see in the structures of the units. Yeah. Any other questions?
Can you just say again the definition of GFAB B?
Sorry?
Just say the definition of GFAB B. It's like the
so GFAB is the Galois group of the maximal abelian extension of F, or the abelianization of GF. GFAB P is the maximal pro P quotient of that. So it's the universal thing for maps into pro P groups.
And can you think of it as the Galois group of something as well?
Yeah, you can think of it as, I guess, the Galois group of the maximal pro P abelian extension or something like that. Yeah.
Cool. Thanks.
Any other questions? Okay, so in the case n equals 1, yeah, because you can twist away the character, and because I don't know, because you're working with because everything's abelian, you can do this explicit deformation theory, lifting theory pretty easily. On the other hand, in general, it's sort of harder, and that is the topic of our research. So let me state our main theorem. Okay, so the main theorem, so this is some of what we prove, and I'll state it in 3 parts. So first of all, this ring, so yeah, I'm going to state the theorem in 3 parts, and then afterwards, I'm going to explain kind of in more detail what each part is really saying or how you should think about it. So first of all, this is a complete intersection ring. And it's flat over O. So in other words, it's pi torsion free, and it is of relative dimension. So relative cruel dimension n squared plus n squared times the degree of the extension f over q. Okay, so relative dimension just means that O is a ring of dimension 1, so the cruel dimension of this entire ring would be 1 plus this, but yeah, it's relative dimension n squared plus n squared f over q. And you can okay, first of all, sanity check, this matches this example, right? Because if I plug in n equals 1, then I get 1 plus the degree, and this mu doesn't contribute to the dimension. So this checks out. The second part of the theorem says that, yeah, and maybe as maybe a quick comment is that this in particular implies that every row bar has a lift to O, which I think is something that wasn't known until in full generality until the paper of Emerton and G, when they introduced their stack, where they give an alternative proof of the stack. So we give a new proof of this existence of just some completely arbitrary lift, at least one.
Sorry, can I take O to be the width vectors without losing any?
The width vectors of what?
K. It's K. What is? I thought rho bar is valued in some finite.
Well, it is valued in a finite field. So what I said, at the beginning, I said that the coefficients have to be big enough So like for the, like strictly speaking, for these theorems to be true, you kind of need like enough room in your coefficients. But like if you started with a big enough finite field, then I think you could probably take limit vectors. Yeah. Although I don't know if f is unramified, if f is ramified to begin with, then maybe you need. Well, okay, for part of the talk you would, and then for part of the talk you wouldn't. So yeah, it kind of depends, I guess. Okay, so this is a theorem about the kind of local geometry of this ring. The second part of the theorem says something about the components, like how does this ring break up into different components? So the determinant map, which I'll write as like this. So okay, what is this map? So if I take any deformation of or any lifting of rho bar, then I can look at its I can take that lifting, take its determinant, and then I get a lifting of the determinant of rho bar, right? And so what I get is if I look at the functor of lifts for rho bar, then it gets a map to the functor of lifts for the determinant of rho bar. And now on the representing rings, everything gets, because I mean these are like co-represented, I guess. So the map on rings gets flipped around. So this determinant map is kind of a it corresponds to the map on functors in the other direction. This map, the claim is that, first of all, this is flat and it induces a bijection between the connected components, not of this ring itself, because I mean, these are local rings, so they're all connected. But if you look at the scheme, like the generic fiber of this thing, so the scheme theoretic generic fiber of this thing, well, okay, I should really put a spec here, but you know what I mean. This induces a bijection. Actually, yeah, let me put the spec so this is not as confusing. I'm really saying something about topological spaces. So yeah, it induces a bijection on the set of connected components of each of these. So it's a bijection between the connected components of the generic fiber of the lifting ring for rho bar and of the generic fiber of the lifting of its determinant, which, as we saw, has a very simple description. So I'll say something a bit more about like how you can use this description to kind of interpret this result after I state the rest of the result. Yeah, and furthermore, so this is a bijection, and these are also in bijection with the irreducible components of, sorry, am I too low? I hope the people on the camera can see. Okay, well, yeah, I'll write this and then move it up in a second. Anyway. So this is a bijection of the irreducible components of spec of R of R square, and each of these irreducible components are normal. So these are normal schemes. And furthermore, this ring, this scheme, the scheme theoretic generic fiber is also normal.
The bar is completely arbitrary.
Completely arbitrary.
Actually, it could be trivial.
Could be trivial, yeah. Could be as reducible or irreducible as you want.
Well, trivial is somehow the hardest case of this.
Sort of. I mean, so I had a paper that I wrote a couple of years ago where I specifically dealt with the trivial case, but it was actually in some sense easier than the case of like reducible, but non-trivial, in the sense that in the trivial case, you can work with the pro-p quotient, the maximal pro-p quotient, like not the abelian one, of the Galois group, and that has like a really nice explicit presentation.
I see.
And so you can just work with that presentation. But
okay.
So if you're not in the trivial case and you don't have that presentation, I mean, there is some presentation, but it's like.
So this statement in that case, you say you can read it off from this pro-p.
Yeah.
Read it off in some non-trivial way.
Yeah, you have to do a bit of work, like in order to get this in order to get this result about components, you have to do a bit of like rigid geometry and connect some points or something. But yeah, it's doable. I mean, okay, strictly speaking, there's an assumption which I haven't said that I'm making, which is that rho bar is like all of its irreducible subquotients are actually absolutely irreducible. But that's fine because you can just enlarge L and that'll always be true.
Sorry, which are in bijection? What is that last bijection?
Yeah, sorry. So the components of this thing are in bijection with the connected components of that thing. And they're both also in bijection with the irreducible components of this thing, like not the generic fiber.
Right, but so what is the bijection implicit in that last statement?
I'm going to explain. Yeah, I'm going to explain how this works. There's one more part of the theorem, and then I'll talk about like what that actually means. Okay, so the third part of the theorem says that so those two things are both publicly available in the archive. This we are not completely done writing up, but we basically have a proof of. If you take the subset of the maximal spectrum of R of R squared 1 over pi. So remember that, like I said this earlier, so this thing, if you look at the scheme theoretic generic fiber, all of its closed points give you p-adic representations, right? So I can take a subset where I impose p-adic Hodge theoretic conditions. So if this is the subset of crystalline points, so basically maximal ideals who, after you mod out by this maximal ideal, you get some p-adic Galois representation, which is crystalline. Then sigma is Zariski dense. Okay, I kind of said this in a bit of a strange way, but this is Zariski dense really in the rigid analytic generic fiber. So what am I saying here? What I'm saying is that, so there's two different sort of ways to consider the generic fiber. One is to take this ring, tensor with QP or L, and then look at its spectrum. And there's a bunch of closed points in that. The other way is that there's an associated rigid space. The points of this rigid space, some p-adic analytic space, are actually in bijection with the closed points in this thing. So they're kind of, I mean, they're different theories and they sort of have different topologies. So topologically, they're slightly different, but at least they have the same points. And if you look at the crystalline points appearing in this thing, those things are actually dense for the Zariski topology in the rigid world. Okay, so if these words mean nothing to you, then I guess just focus on the first two parts. But this is, I mean, this is some statement about like density of points that have conditions that correspond to something that you might see on the automorphic side when you're doing a modularity lifting proof.
But you're allowed to use any weights.
Any weights, yeah. I don't have any restriction on the Hodge state weights of the representation. Okay. So let me try to actually explain what's going on here. So how do you think about parts? Let me check the time. So yeah, how do you kind of think of these things? So the first thing is kind of like an underivedness statement. Underivedness statement. And what I mean by that is that there's a recent construction due to Galois and Venkatesh of a derived version of this deformation theory, where instead of using like Noetherian rings, you use simplicial Noetherian rings, and then the deformation ring you get out of it is some complicated derived like simplicial ring thing. And what I'm claiming here is that since this thing is complete intersection, the corresponding derived ring that you would get if you set things up correctly is homotopy equivalent. So in other words, it doesn't carry any extra data than it's homotopy equivalent to this classical underived ring. Okay, so there's no derived structure in this picture. Like if you did a derived version of this, you would get no extra information. So that's one way to read part one. Another way to, okay, so what is this business about the determinant map? Well, so if we look at the structure of this deformation ring in the n=1 case, right? You have a bunch of power series variables, and then you have this thing mu, right? So mu is a finite group. It's the group of p power roots of 1 in the field. And so I get maps from O mu to r det rho bar squared to r rho bar squared. Right. I mean, this is the determinant map, and then this is just the natural way to view this as an O mu algebra. And but what my claim is that the irreducible components sorry, 1 second. Yeah, what I'm claiming is that the irreducible components of r rho bar square are exactly the rings. Sorry. So okay, first of all, yeah, we have this first map which goes from O mu to r det rho bar square. If I want to look at the irreducible components of the determinant ring, these are exactly the things that you get when you take r det rho bar squared and then you tensor over O mu with O, where mu and this map is some character chi, which is the character of O cross. So basically what I'm saying is that like this thing is not irreducible if mu is non-trivial, but if you want to find the irreducible components, you can just fix characters of this trivial of this finite group, and then taking the quotient by like taking the sort of co-invariance of that character give you all the irreducible components. And so what that means for the deformation ring is that I take r rho bar squared. First, let me invert P, and then I look at the structure of this thing. So remember, I said something first about the set of connected components of this thing. And what I'm claiming is that this ring, this decomposes into a product of rings over these characters of mu into r rho bar squared chi 1 over pi, where r rho bar squared chi is r rho bar square tensor over, again, O mu with respect to chi with O. Okay. And so sorry, this still looks a little abstract, but let me try to give you an explanation of how you would identify what, like given a point in the generic fiber, how would you actually say what component it's in? So this is kind of the maybe better interpretation of the statement. And the point is that if I pick some closed point in the generic fiber, so the maximal spectrum of this thing with P inverted, then, okay, then out of this, as I explained before, you get a Galois representation rho x, which goes from GF to GLN of K, where K is some finite extension of L. And then what I can do is I can look at the determinant of rho x, and I can restrict it via local class field theory to mu, right? So there's the Artin map, which goes from the units in F to the abelianized Galois group of F, and this is a determinant, so it's really a representation of the abelianized group. And then I can restrict it to mu, and so I'm saying rho x lands in, well, it lands in this. It lands in this component. So it lands in the chi component. If and only if, when you compute this restriction, this is equal to chi, right? So what I'm saying is that if you want to figure out which component in this generic fiber you live in, you just take the representation, take its determinant, restrict to the torsion part, this p power torsion part, and look at what you get. And that tells you where you live. Okay. Any questions about that? Cool. All right, so in the remaining time, which is about 15 minutes, I'll try to go over some of the ideas of how you prove this theorem.
Just a real quick question about the statement. Like, is it like effective in the sense, like, can you algorithmically produce, so you say it's a complete intersection ring, can you algorithmically produce the data that verifies that? Like,
yeah, so I'm going to say something about this in a minute. I mean, in principle, you could, but the way we do it is not quite as direct. Like we do end up with some presentation, which I think in principle you could probably make explicit. I'm not sure. I'm not sure the extent to which you could literally put it on a computer and do it. But yeah, let me say a bit more about this in a second. So. Okay, so yeah, let me talk about some ingredients which go into the proof. So I guess kind of the first step to even make sense of why, so the first step to make sense of this complete intersection property is to study what in Galois deformation theory is called tangent and obstruction theory. So this is something that comes from classical deformation theory of schemes. It is kind of a general principle in whenever you deform anything, really. The result of this theory gives a presentation of this ring as a power series ring mod, mod some ideal with some generators where R is the dimension as a K vector space of the, well, there's two ways to think about this thing. The first way is maybe not so important for what I'm going to say, but I'll say it anyway. So this thing, if you take this functor and you plug in the ring of dual numbers, kx mod x squared, this turns out to be a K vector space and has some dimension. This thing is also isomorphic to the first continuous Galois cohomology of GF with coefficients not in row bar, but in its adjoint representation. Okay, so you take the representation of 2 by 2 matrices, or sorry, n by n matrices over K, and then GF acts via row bar by a conjugation. Okay, and that's some K vector, and then you look at the cohomology of this representation, and that's some
plus n squared or something.
Sorry?
Plus n squared or something, right? You have a framing.
So this is right, and the reason is that if you didn't have the framing, you'd put a 0 here, and then you get the right thing. Like if you didn't have the framing, then you'd have to fix the determinant, and then.
But okay, we can.
Yeah.
It makes no difference.
Sorry. No, you're right. This is it's basically 1 cocycles. Yeah. Sorry, I was confused. Yes. Yeah, the space of 1 cocycles gives you this. So it's some cohomological quantity, but yeah, as you say, the co-boundaries correspond to kind of conjugation. Yes. Thanks for that. So R is equal to the dimension of this Z1, and then S is equal to the dimension of, okay, this time really H2. So, yeah. So these are some cohomological quantities of the sort of intrinsic to the representation, which tell you, with some formal theory, give you an explicit presentation. So this is what I mean by explicit. I mean, it's not, it depends on how effectively you can compute these things, which maybe you can. I don't know. And right, so what does this tell us? This tells us that the dimension of this ring is greater than or equal to 1 plus R minus S, right? I mean, this power series ring is dimension 1 plus R, so 1 and then R, and then, okay, you're killing S things, some of which can contribute to lowering the dimension and some of which won't. But if you want this to be, if you want to show that this is a complete intersection, it suffices to show the other direction. So this thing is actually bounded above by the dimension of 1 plus R minus S. And you can actually so this thing has by basically the local Euler characteristic formula, this thing is the same as n squared plus, 1 plus n squared plus n squared times the degree of S. Okay. So what, in order to prove part 1 of the theorem, you just have to show, besides normality, you just have to show that the dimension of this thing is bounded above by this quantity.
Sorry, flatness.
Flatness. Yeah, right. There's also flatness.
Sorry, did you say it's normal?
Sorry, I don't mean normality of. Yeah, okay, sorry, ignore that. Yeah, flatness is the other thing. Yeah, yeah, sorry, normality is not of this thing, but its components, but yeah. Right. All right, so how do you actually do this? So this is kind of the most technical part of the paper. So I'm not really going to give many of the details of how you do this step, but I'll tell you some of the main ingredients we use. So it turns out it's convenient to work with, instead of representations, we work pretty well. We use some existing results due to, Böckle and his former student, and Princeton Juschka on Galois, like deformations of pseudo representations. So what is a pseudo representation? If you take a representation, which is, it's a map from a group to some invertible matrices, and you just take the characteristic polynomials of each one of those matrices and only remember that data. I mean, you have to be a bit more careful. Like there's some structure, satisfied by these characteristic polynomials. Then you can package that data into what's called a pseudo representation. And yeah, it keeps track of the characteristic polynomials of a representation. And so like if you're over an algebraically closed field, there's like a unique semi-simple lift of each one of these pseudo representations. So it's kind of like, at least geometrically, it's kind of like over geometric points. This is a way to, just keep track of the semi-simplification. And yeah, so like associated to rho bar, there's something which I'll call D bar, which is its associated pseudo representation. And okay, this D bar also has a deformation functor, so I can deform D bar into pseudo representations over these Determinant rings. And then this thing turns out to be representable, and so I get a pseudo deformation ring, which is kind of like one of these lifting rings, but instead of representations, it's pseudo representations. So this is the pseudo lifting ring or pseudo deformation ring of D bar. And so what we do in the paper is we look at, so first of all, there's a map to R rho bar squared, right? And this is, again, a kind of inverse map to taking a deformation and looking at its associated pseudo representation, right? So that's just kind of keeping track of the characteristic polynomials morally. We factor this map through something which we call AGen. Okay, so what is AGen? AGen represents the moduli space of representations of GF. Representations of GF. But now the coefficients are actually in RPS algebras, so RPS D bar algebras. And moreover, we require that these representations have associated pseudo rep equal to the universal pseudo representation, right? So if I have a deformation problem and it's representable, then I get some universal pseudo representation with coefficients in this thing. And so now what I'm saying is you can look at representations, like honest to God representations of GF, valued in algebras over this universal pseudo deformation ring, and you can require that their associated pseudo representation is equal to this universal one. Okay, so I mean, and when I say equal to, I mean you push forward along the coefficients into the algebra, and they should be equal there. The advantages of working with this thing are twofold. One is that this map is a completion. Right, so I mean, okay, AGen, right? AGen is a moduli space of this form, and AGen has a point corresponding to rho bar, just by definition, right? Because rho bar has pseudo representation D bar, and DU lifts D bar. So rho bar automatically lives in the spec of this ring. And actually, if you take that closed point in this space and you take the complete local ring, it turns out you get R rho bar squared. So this is one of the things we show. And then we also show that this, or well, okay, and then it turns out that this map, so this isn't something we show, this is something we use, is it's a finite type. Okay, so AGen is a finite type algebra over the pseudo deformation ring. So why is this useful? Make sure I'm not going over. Okay, yeah, maybe this is the last thing I'll say then. Yeah, so why is this useful? So, okay, maybe this is the last thing I'll talk about. So the point is that if we want to make a dimension estimate, first what we do, okay, so for reasons that I guess I don't have time to explain, we work in the special fiber of this ring. So we look at characteristic P deformations of rho bar. This is for reasons having to do with like making the most efficient way to prove kind of normality and do this decomposition of irreducible components. But we take this pseudo deformation space mod P, and then we decompose it into a union of locally closed subschemes. And these are, I mean, you can kind of think of these as reducibility strata. So if you take a pseudo deformation, a pseudo representation, over an algebraically closed field, this thing has a unique semisimple lift to a representation. And that representation, you know, it has some reducibility structure, right? It has some constituents. And so the pseudo representation sort of decomposes into what are called irreducible pseudo representations over an algebraically closed field. And these UIs correspond basically to the size of the Jordan-Holder blocks you get of those representations. And you know, like maybe the ordering of them as well. So then so this work of Böckle and Juschka lets you say something about the dimension of each of these UI. So they give a precise formula for the dimension of each of these things. Okay, and then if you understand this thing and you want to understand R of R squared, well then this is just a completion of this. So it suffices to understand AGen. And it turns out that if I look at spec AGen mod pi, well, okay, this thing is a moduli space of representations, and so it has an action of GLN by conjugation, right? And I can look at the GIT quotient of the action of GLN on this space. This has a map to the pseudo deformation space mod P, and this thing, it turns out, is not an isomorphism, but it's at least a homeomorphism. I mean, there's some issue with nilpotents and things, but this is at least a homeomorphism. And so I can study the dimension of this thing by understanding the dimension of the strata and then working over the fibers of points in the strata. And to try to understand the fibers of points in the strata, you do a similar thing. You kind of break up like the fiber over some, like the geometric fiber over some point in the space is some pseudo representation. You break it up into its blocks, and then you do some deformation theory of each of those individual blocks, and you can obtain some bounds that way. Yeah, so I mean this observation that this is like the GIT quotient allows you to use some GIT theory, which I mean kind of works because this is a finite type map. And then yeah, you can split up this study into something about the fibers and then something about the target. So I didn't get to say anything about the proof of irreducibility, but I think I'm out of time, so I'll stop there. Thank you.
Are there any questions for Ashwin?
So what's the input into this work of Böckle and Juschka then? I mean, that seems to be kind of essential.
Yeah, it's completely essential. It's kind of the basis for this whole argument. And they study the deformation theory of these pseudo representations using so I'm not intimately familiar with that paper in all of its details, but they use Clifford theory in an essential way. The idea really is that like if you want to understand these reducibility, these like strata, you can split them into their smooth loci, and then their singular loci. The smooth loci are kind of easy to deal with. The singular, because their deformation rings are smooth, and then you can use some like take duality to explicitly compute what that dimension should be. The issue is that if like the singular locus is different because the sort of deformation rings of the singular points are no longer smooth. So you want to just try to like make the prove that singular locus is really small. And so you need a characterization of the singular locus. And that characterization, like so on the generic fiber, that characterization is just saying that the representation is reducible. And that follows from some H2, H0 kind of computation. Mod P is not quite so simple. It's either reducible or induced from some degree P extension, the representation. And so you have to do a bit more analysis to kind of understand what's happening with the special fiber.
But for example, for the trivial representation, you said you had done this before.
Yes.
So this gives some new argument. Is that right?
Yeah.
Oh, no, it's purely local, this whole argument. It doesn't involve any global methods. But
everything's local, yeah.
It doesn't involve use of presentation.
No, I mean, it doesn't involve the use of a presentation of the group. All it involves is this.
Right. I see.
Yeah, I mean, for the trivial representation, I use the fact that GF ab P is like generated by some number of generators mod some commutator equation thing, which you can then like kill a bunch of the variables in the commutators and then get simple things.
Are there any more questions?
Can I ask a question? So analogous to the second part of your theorem, if instead of determinant, so you take your R rho bar square and then, so given a rho bar and take say symmetric square or symmetric cube or any symmetric bar. So then there's a map from R sim k rho bar square to R rho bar square. So can you tell anything about this?
Off the top of my head, I'm not sure. Yeah, I mean, this taking the determinant map is really the only kind of functoriality that I understand. I mean, you could sort of imagine trying to do this for other groups or other settings, but I don't. I mean, I think part of the reason that this argument works, to my mind, or like the boundaries of my imagination for now, are that the GL1 case is incredibly simple, and so this is just a question of comparing something more complicated, which we still don't fully understand. Like I don't claim to understand the singularities of like each of these components. Like I can give an upper bound on what their dimension should be, but like within that locus, I don't really know what's going on. So comparing other contexts to this context, I'm not entirely sure how it would work, but conceivably you could maybe say something about just the connected components.
Any more questions? Any questions from Zoom, maybe? Cool. All right, let's thank Ashwin one more time.